Assalamu alaikum and a very good day to all of you. My name is Matsaini bin Keton. Now, have you ever looked at a massive skyscraper or a really long bridge and just wondered, how in the world is that thing still standing? What are the invisible forces holding our world together? Well, that's exactly what we're going to dive into today as we begin our journey with MEC111 Engineering Mechanics, focusing on the amazing world of statics.
Okay, let's just jump right in. Take a look at this incredible piece of engineering on your screen. This is the CCTV headquarters in Beijing. I mean, wow. It's a huge, complex building that totally seems to defy gravity, doesn't it? It's like these two giant towers are just leaning on each other, held up by nothing but pure design genius. So, the big question, right? Why doesn't it just topple over? What are the hidden rules, the forces at play that keep this whole thing, and really everything around us, from just collapsing into a pile of rubble? The answer? Well, it all comes down to the world of mechanics. And to really understand how things stay put, we first need to start with the big picture, the parent field, which is mechanics. You can think of this as the fundamental rulebook for pretty much everything we're going to talk about. So, what is mechanics, really? Well, the official definition says it's the physical science dealing with the state of rest or motion of bodies under the action of forces. But what does that actually mean in plain English? It's simple. It's the science that looks at any object, from a tiny screw to an entire planet, and asks two basic questions. Is it moving, or is it standing still? And what forces are making it do that? That's it. It's the physics of pushes and pulls. Now, once you step into the world of mechanics, the path immediately splits in two. You have two main branches. You can think of it as the study of things that don't move and the study of things that do move. And these two branches have names, statics and dynamics. And here's the difference, side by side. On the left, we have statics, and this is going to be our main focus. It's all about bodies that are at rest. There's no acceleration, and all the forces are perfectly balanced. We call this special state equilibrium. Then on the right, you have dynamics. That's the exciting stuff. Bodies in motion, things speeding up or slowing down, where forces are unbalanced. And this image right here, it's the perfect way to see that difference in action. On the left, you've got the Penang Bridge, a massive, solid structure that's designed to do one thing, stay exactly where it is. That's a classic statics problem. On the right, a Ferris wheel, constantly spinning, its cars moving and accelerating. That is pure dynamics. For us, in this course, our world is the bridge. All right, so now that we've zeroed in on things that don't move, let's get to the absolute heart of statics. This is the single most important idea that makes the whole field work. It's called the principle of equilibrium. So here's our official definition. Statics is the branch of mechanics that deals with bodies at rest because the forces acting on them are in equilibrium. Let's put that in even simpler terms. Statics is the science of stability. If something isn't supposed to move, well, that's a job for statics. And this is the golden rule. This is the one key condition that defines everything in statics. It looks simple, but it's incredibly powerful. That little symbol, sigma, just means the sum of. So this equation, sigma F equals 0, just means that if you add up every single force acting on an object, every push, every pull, gravity, the support from the floor, they all have to cancel each other out completely. The grand total has to be 0. You know, to make that more intuitive, just picture a game of tug of war, right? If you have two teams and both are pulling on the rope with the exact same amount of force, what happens? Nothing. The rope doesn't move an inch. That rope is in a state of static equilibrium. Every single force is being canceled out by another force that's equal and opposite. And that imaginary tug of war, that is exactly the job of an engineer designing a real-world structure. Think back to that bridge. Every car that drives over it, every gust of wind that hits it, even its own massive weight, those are all forces or loads trying to pull the rope. The engineer's job is to design the supports to pull back with the perfect amount of reactive force to keep that rope perfectly still, ensuring the bridge is stable and safe. Okay, so now that we get the main idea, let's go have a look around. Where do we actually see this principle of balance in action? Because I'm telling you, once you know what to look for, you start to see it absolutely everywhere. Of course, we see it in every single bridge ever made. Their whole point, their entire reason for existing, is to stay perfectly still while carrying huge, changing loads from traffic and weather. It's a massive, high-stakes balancing act. And we're back to this amazing building. The reason it doesn't fall over is because a team of engineers sat down and painstakingly calculated every single force, from gravity to wind to the weight of the people inside, and then designed a structure that creates the perfect opposite forces to cancel everything out, keeping the whole thing in perfect equilibrium.
But hey, this isn't just about giant, expensive projects. Statics is happening all around you, right now. Think about a car parked on a hill. What's stopping it from rolling away? The static friction in the tires is perfectly balancing out the pull of gravity. Or that lamp hanging from your ceiling. Its weight is perfectly balanced by the tension in the cable. Even the very chair you're sitting on at this moment, yep, that's statics. It's providing an upward force that exactly matches your weight.
So this all brings us to the big "so what" question. Why do we as future engineers spend so much time studying things that don't move? What's the real point of mastering this idea of equilibrium? Well, here's why it's so critical. First, and most importantly, statics is the language of safety. If your equilibrium calculations are off, buildings and bridges can fail. It's that simple. It's also the key to stability, making sure our designs are tough and reliable. It helps us with efficiency, so we use just the right amount of material without being wasteful. But maybe the biggest reason is that statics is the foundation. It is the absolute first step you have to take before you can design almost anything else in mechanical or civil engineering. So I'll leave you with this final thought. Take a moment, right now. Just look around the room you're in. Look at the walls, the ceiling, the table, the chair. Now that you understand the principle of equilibrium, you can start to see all the invisible, perfectly balanced forces that are holding your entire world together. So what's holding it all together? The answer is statics.